Let's start just like second lecture of the by Masanori Tanaka about the first order phase condition. We start.
Yes, thank you very much. Yesterday, we discussed how to obtain the effective potential at the finite temperature system. And today, we discussed how to understand the dynamics of the first order electroweak phase transition. So first, let's confirm the let's open the discussion down yesterday. As we confirmed yesterday, so in order to realize the first order phase transition, the potential barrier between the false vacuum and true vacuum plays an important role to realize the first order transition. If such potential is realized, then the tunneling can be realized at a certain temperature. So today, we discuss how to evaluate the tunneling rate by using the effective potential defined by finite. So first, let's consider let's assume that this state we write the phi z. And as a final state, so we write state as a phi t. If the tunneling process occurs, then it means that we should consider the time evolution to the ket phi 0 to the ket phi t. So in the quantum mechanics, such time evolution is realized. It can be expressed by this form. Like this. So this form is well known, the quantum mechanics. And then this factor E is generally interpreted as an energy. And then, let's consider the case where the energy has an imaginary part. So then what happens? So if the energy has an imaginary part, this formula can be expressed by this. The real part, the energy, and the imaginary part of energy. So like this. We assume that energy has an imaginary part and the real part. And then let's consider the inner product of this scale. Then we can obtain that if we consider inner product, the imaginary part is factored out. So mean that exponential we can obtain this formula. So this result means that in order to realize the tunneling, then the imaginary part of energy is very important. So also, if the energy has an imaginary part, such tunneling process can be realized. So therefore, we naively expect that the tunneling rate is expressed by this one. So this expectation is related to the decay of the particles. So this is a very naive explanation. However, so the Coleman, Stanley Coleman, confirmed that he thoroughly calculated the tunneling rate in the quantum field theory, and he showed that this equation is valid, but only the at zero temperature. So it's only valid at the zero temperature. But in order to discuss the first order phase transition, so we should take into account the thermal effect. Then how about the temperature system? According to this relation, so first we naively expect that at the final temperature, the tunneling rate can be expressed by the F. The F is a free energy evaluated at the final temperature. So at the zero temperature, the tunneling rate is expressed by the energy. However, so when we consider the thermal correction, then the tunneling rate is characterized by the free energy. So, and the validity of this equation is shown by many theorists. So, but proving this relation is it takes a long time. So therefore, so this time is limited. So I will skip this derivation. So we just assume this equation is valid. And in this lecture, so we extract the physical meaning of this relation. Just extract the physical meaning.
Derivation is given by some references which you gave yesterday.
Okay, so I should show the difference. The difference is different. So this one, this equation is derived by the code. So so I forgot the number of the difference.
That's fine, but below one.
Below. Okay. So 3. So this formula is varied by the applet. So however, so I forgot the date, but the applet derived this equation. The paper, I think that his paper is physical relativities. So this relation is important in this lecture. And so in order to evaluate the tunneling rate, so this relation indicates that so we should evaluate the free energy. Okay, so let's evaluate the free energy in the scalar field theory in this lecture. So, and so in order to discuss the tunneling rate, so in this lecture we focus on we use path integral formalism. So it means that the partition function for the scalar field theory can be expressed by this. In general, expressed by this. At the final temperature system. In the past integral formalism, the partition function for the scalar field theory can be expressed by this. And n prime is constant, so which does not have a physical meaning. So here we should integrate the stellar field configuration by the path integral. And S3 is defined by this form. So the definition of the S3. So S3 is the four-dimensional Euclid action. Euclid action. And so the VEFT is a effective potential evaluated at the final temperature. So yeah, discussed yesterday. Okay, so therefore, so in order to evaluate the tunnelling rate, so we should obtain the partition function for the scalar field theory. And then, so let's evaluate the SE. And here, so in order to simplify the calculation, so we assume that the high temperature limit so it means that beta, so which corresponds to the inverse of the temperature, therefore the beta, beta is sufficiently small.
Sorry, I'm a bit confused. So when you write down the gamma data,
Like this?
yeah, so you have written imaginary F. And here, so F is defined by log Z, right?
Log, yes, exactly, yes.
So by definition, so this zeta,
Mhm.
the partition function is real in this case. If you start from the Euclidean partition.
No, so when we consider the non-trivial field equation, so the distribution partition function has an imaginary. So we will confirm later. So
Okay.
yeah. Let's consider the high temperature limit. So this limit means that so let's focus on this integral. So because since the beta is very small, therefore so we can regard this integral approximately by this one. So we do not have to integrate the term. And also since we are considering this limit, therefore we naively expect that the dependence of the scalar field is also negligible. Therefore, in this analysis, we assume that these two the condition. Then the SE can be expressed by so since we can neglect the first term, the SE can be expressed like this. And we define the S3 by using this form. Therefore, so you have to obtain the SE, so we should calculate the S3. S3 is a three-dimensional effective action. Three-dimensional action. And okay, so the free. So in order to realize the tunneling process, so we expect that the the field configuration with minimal action. Field configuration. With the condition for the such field configuration is expressed by this form. So if the non-trivial solution can realize the minimum effective action, then field configuration should satisfy this stationary condition. So by using this formula, so we can obtain that this field equation for the scalar field. By using this, so we can obtain this field equation for the scalar field. We call the non-trivial solution of this field equation as a phi b. So therefore, we write the non-trivial solution as a phi b. The phi b can satisfy this field equation with a certain boundary condition. So then, so let's consider the let's evaluate the action for the non-trivial solution phi b, and we write the non-trivial solution, the action for the non-trivial solution as a SE1. And SE1 it can be expressed in general. The SE1 can be expressed by like this. So it can be expressed like this. So we this one. But the phi b can satisfy this condition, therefore we can neglect this term. Therefore, so we should take into account these two terms. And by using this action, so we can evaluate the partition function. And the partition function can be expressed by this one. So in the first step, so we write the uh, partial function in terms of the path integral for the pi. However, so in this step, so we change the path integral as a delta phi. Delta phi, the general field can be expressed by the fluctuation around the non-trivial solution. So we should do the path integral. So for the in terms of the delta phi. The most important point is that the delta one includes this exponential one. So as we will see, so this factor can play an important role when we discuss tunneling. We discussed the partition function for the non-trivial solution. However, so we have of course an trivial solution. Trivial means that the phi is always exists at the origin of the potential. So this is also the solution of this field equation with a certain boundary condition. So when we evaluate the four-dimensional action for the trivial solution, then so if you calculate it, then you can obtain this final result. So I'd like to note that for the non-trivial solution case, the first term can increase. However, so for the non-trivial solution, we do not have to consider the first term because if we define the effective potential like this, then so you can confirm that the first term is always Z if we define the potential like this. So the important definition is that the potential at the origin is always Z. If you define the potential like this, then so you can check the first term. I cannot take into account. Okay, so since we obtained the action for the trivial solution, so we can evaluate the partition function for the trivial solution. So like this. In the first one, so this derivative is evaluated at around the non-trivial solution. So, however, for for the case of 0, its derivative is evaluated around the trivial solution. So we obtain the non-trivial solution and trivial solution in this field equation. Therefore, in general, the partition function, general partition function is expressed by summation of Z3 and Z1. But so since we are interested in the case where the field configuration, so the field configuration at the initial time should be at origin, because we are interested in the tunneling from the force vacuum to the true vacuum. Therefore, we assume that the partition function, the trivial solution, the value of the trivial solution should be sufficiently large, larger than the value of the Z1. So this is the assumption for the first order expansion. Then by using this formula, so we can evaluate the free energy. The definition of the free energy is given by. And by using this approximation, so we can express the free energy like this. The second term probably includes Z. So as I emphasized, so in order to realize the tunneling process, the imaginary part of the free energy plays an important. And so actually, so you can confirm that the imaginary part of the free energy comes from the second term. So because if you evaluate the fluctuation around the fluctuation mode around the non-trivial solution, then you can find that. So if you simply write the fluctuation mode around the non-trivial solution as a omega 1 sphere, then so if you evaluate the omega 1 by using the non-trivial solution, then so there is a one negative eigenstate. Negative eigenstate means that omega. So omega sphere can be negative. So as a result, so Z1 can include the imaginary part. So I cannot check the value of the negative pole. So this time is because the time is limited. So yeah, but you can check that the Z1 can include the imaginary part. Yes, we did.
So yeah, I understand that is a negative node.
Mm-hmm.
And naively, so this integration is divergent because the exponent is positive. Right?
Mm-hmm. Yes. Mm-hmm.
So when you want to get finite results,
Mhm.
so we have to analytically
Yes, exactly. Yes.
So that's why you have imaginary.
Yes, exactly. Yes.
Okay.
Yes. So therefore, as a result, so we can obtain the tunneling rate. Uh, so, okay, so we can obtain the imaginary part of the free energy can be expressed by this form. And as we have checked, the Z1 has this exponential factor, and this exponential factor is a leading. Therefore, so we should take it as the contribution from this effective from exponential. As a final result, so we can obtain that the tunneling rate at a finite temperature system can be expressed by this. The coefficient of A it can be determined by by calculating the whole analysis so carefully. But yeah, in this lecture we do not discuss the detail. But anyway, so the tunneling rate at the finite temperature system can be expressed by this form for the first order phase function. So in order to evaluate the gamma, so we should solve this field equation, and we should obtain the trivial, non-trivial solution finally. And for simplicity, in this talk, so we focus on the solution. Solution. Is a spherical symmetry. So it means that this non-trivial solution only depend on the radius from the origin. So R is defined by the absolute value. So it is well known that such a spherical symmetric solution can give a minimal action. So therefore, this assumption is reasonable. So then, this field equation can be expressed like the equation can be expressed by this one. So, yeah, in order to evaluate the gamma, so we just solve this field equation. But of course, we should take into account the boundary condition. And the boundary condition is given by this one. So, because since this equation includes the second derivative, so therefore So we should take into account the two boundary conditions. The first one is like this, and the second one is we will find the solution with these boundary conditions. And this first boundary condition is required to obtain the finite action, finite number action. So to get the finite action. So because since so by assuming this boundary condition, so you can find so you can make the action the finite. And this second boundary condition is required to avoid the singularity. Singularity has the origin. So I will explain the meaning of the condition. And so let's consider the case where this boundary condition is not satisfied. So it means that the origin is not. Then, for example, so we can obtain the like this boundary condition. For example, since the derivative at the origin is not zero, so we may find such solution. So this function is expressed in terms expressed by the radius. However, so when we consider the three-dimensional space, then this solution can be expressed by this. If this condition is not satisfied, and then in general this non-trivial solution has a cusp structure. So therefore, the singularity can appear as the origin of the of this boundary condition. The singularity as the origin of the non-trivial solution. So in order to avoid such structure, so we should consider this second boundary condition. If you solve this field equation with its boundary condition, in general, so you can obtain like such solution. At the origin, the derivative is already zero. On the other hand, at the large line, for the outside, the value of the phi is always zero. So we often call such solution as a bound solution. So once we obtain the bound solution, then so we can discuss the tunneling rate. And by using this tunneling rate, so we can discuss the dynamics, the first order explanation. Therefore, so to evaluate the bound solution is very important. when we discuss the dynamics of the first order phase transition. So in this lecture, so I cannot explain how to obtain this bound solution. So numerically. So however, so if you are interested in, so I will discuss the detail of how to evaluate this bound solution. So numerically. Okay. And then, so what is the physical meaning of this bound solution? The physical meaning is that like this. So let's consider the universe. So when the other temperature is getting low, then the first order phase transition can be here. Like this. So the outside of the bubble, the symmetry is not broken. However, the inside of the bubble, the symmetry is already broken. So let's consider the field configuration around this direction. So this field configuration corresponds to the bound solution. So therefore, this vacuum bubble is just the bound solution. Therefore, when we discuss the properties of the vacuum bubble nucleated at our universe, then so we should analyze the properties of the bound solution. Okay, so far, so we discussed the how to obtain the bound solution, and this part was mathematical. So next, I'd like to discuss the physics for the phase transition. Let's consider the parameters which characterize the dynamics of the first order phase transition. In the conclusions, there are four important parameters. So I will explain detail. So, however, the dynamics of the first order phase transition is generally described by these four parameters. In the following, I'd like to discuss the detail of these four parameters. So once you obtain the value of these parameters, so you can discuss any property of the first order phase transition in principle. Okay, so first I will explain the nucleation technology. Nucleation temperature is defined by T. So at the Tn, so Tn is defined by this equation. The gamma is a tunneling rate for the first order phase transition. and H is a Hubble factor. The nucleation temperature is defined by this formula. And the physical meaning of this condition is following. So this figure shows a universe, and each box represents a Hubble function. One Hubble function. For horizon. When the temperature is higher than the nucleation temperature, then the phase transition may only realized in severe in a human. However, so when the temperature becomes Tn, then so at least so one vacuum bubble is nucleated at each Hubble function because gamma is a tunneling rate in the per volume and per time. Therefore, we can consider the multiplication for the gamma in volume. Then so this equation is that at least the one vacuum bubble is nucleated at each Hubble volume. So this is the definition of the nucleation. So if the gamma over H4, this value is always smaller than the unity, so it means for any temperature. So it means that the phase transition cannot be completed by step. So therefore, when we discuss the realistic new physics model, so we should satisfy this condition at a certain temperature, at least. So therefore, this condition gives the theoretical bound for the new physics model with the first order phase transition. So you can use this condition as a theoretical constraint. So when you write the papers. So this is the first important quantity for the first order phase transition. The second one is the duration of the phase transition. Phase transition. So this is expressed by the beta parameter. And we confirm the tunneling rate is expressed by this form, approximately expressed by this. And this it can be expressed like this consider where the SE four-dimensional action can be expressed by the beta parameter and delta t. So delta t is a typical duration of the phase transition. Therefore, the beta characterize the duration of the phase transition. Strictly speaking, the beta inverse characterize the duration of the phase transition. And then the beta parameter is defined by this form. So derivative of the four-dimensional action at the t. So Tn is correspond to the Tn. So as we confirm the Tn is defined by this form. The Tn is time with this function. And this equation can be expressed by like this. So you can check in this equation. So here is the temperature and H is the power. This value is evaluated at the nucleation. And so we define the normalized beta parameter as beta over H. So therefore the beta parameter that can be calculated by evaluating the three-dimensional action for the bound solution. So therefore, so once you obtain the bound solution, so you can calculate the beta parameter. And third one is latent heat. Reduced by the first order of definition. So we write the latent heat as alpha zeta. In general, when the first order phase transition occurs at the early universe, the released the latent heat can be released like this form. So the delta V is a potential difference between the false vacuum and true. And the delta S is a change of the deviation of the entropy when the phase transition occurs. And this can be expressed by you can obtain this form. And the alpha parameter is defined by the like this. Because so therefore the alpha parameter characterizes the ratio between the radiation component and the vacuum energy component, the energy density for the vacuum energy. And this latent heat is also obtained when you get the bound solution. Therefore, the alpha parameter is also determined by the bound solution. And finally, so for velocity, so we write VW. So when we discuss the prediction of the gravitational waves, the ball velocity plays an important. However, so to get the ball velocity is very difficult because in order to determine the ball velocity, so we should consider the interaction between the interaction between the vacuum bubble and the plasma. So when the vacuum bubble is nucleated at the early universe, then in general this vacuum bubble can expand. Then this vacuum bubble interact with the plasma, and the plasma gives the friction to the vacuum bubble. So therefore, so in order to evaluate the ball velocity, so we should take into account the interaction between the ball and the plasma. So such calculation is very difficult. Therefore, in general, the ball velocity is taken as a free parameter. So it's often assumed as a free parameter in many papers. Okay, so as we explained, first the properties of the first order phase transition can be determined by these four parameters. And these parameters are generally determined by the bound solution. So finally, so I'd like to discuss the gravitational waves from the first order phase transition. First order phase transition. As we explained, as we confirmed, the first order phase transition at the early universe proceed near the nucleation of the vacuum bubble. Or the bound solution. The expansion of the bubble. As shown in this figure. And when the phase transition realize, of course, there are many vacuum bubbles, and they are expanding. And at a certain time, so these vacuum bubbles collide each other. Then the gravitational waves can be produced. Is a symmetric phase. Inside each sample, the symmetry is already broken. And so when we discuss the gravitational waves from the first order phase transition, and so there are the three sources of the gravitational waves. The first one is comes from the collide, the collision of the vacuum bubble. The gravitational waves can be produced by the collision of the vacuum bubble. And the second one is the turbulence. When the first order phase transition is realized, the non-thermal equilibrium situation is realized. Therefore, in general, turbulence can be produced. such turbulence can produce the gravitational waves. So when the vacuum bubbles fry, then the sound waves also produce. Then this sound waves also gives the back gravitational waves. Sorry. So these are the main source of the gravitational waves produced by the first order phase. In the following, I will explain the property of the gravitational waves. So, the gravitational wave energy. So here, so we assume that gravitational waves propagate so here special polarization. So in general, when we discuss the gravitational waves, we often the fluctuation around the so eta mu nu is a metric in the Minkowski state, and h mu nu is a fluctuation around the flat space. So instead of this, so we assume this condition. So it means that the matrix is generally it can be expressed by this. Can be expressed like this. So this condition indicates that so we do not have to consider the time component of the fluctuation around the flat metric. So because if, for example, if such component is not zero, then it indicates that our universe has a special direction. So such a special direction is determined by the gravitational waves. However, since we are interested in the gravitational waves from the first order phase transition, therefore, so we naively expect that the produced gravitational waves does not have a certain special direction. So therefore, such component such component is not needed. So therefore, so we assume this condition. And we do not reject this equation. However, so we just use the result of the general relativity. So the energy density of the produced gravitational waves can be expressed by this one. So this formula is often called as Isaacson formula. This bracket means so this bracket means time average. Bracket means time average in a produced gravitational wave P. So in the following, by using this formula with the dimensional analysis, so we discuss the property of the gravitational waves. So when we discuss the gravitational waves, of course, we should consider the Einstein equation. The Einstein equation, so by using this method, the Einstein equation can be expressed by this formula. Since we are interested in the qualitatively property of the gravitational wave, therefore, so we do not take into account the the factor, contribution of the factor. This is the prediction, Einstein prediction. And by using this formula, so since this part this the Lambert has an order on the beta square. Therefore, by using this formula, so we expect that the time derivative of the Hij is expressed by this form. The time derivative can be expressed by using the typical time scale of the phase transition phase. And by using this Einstein equation, then so we can obtain this expression. The time derivative of the Hij is determined by the energy moment of this. The other hand, the gravitational waves from the energy density of the gravitational waves is zero. Is expressed by and by using this formula, so we obtain the in general, the phase transition should occur at the radiation dominant universe. Therefore, the Newton constant can be expressed by using the Hubble parameter and number energy density, critical energy density. By using this result, so we can obtain the W. So which is this is the amplitude of the gravitational waves. And this value as a ratio between the rho GW and rho critical. So by using this result, so you can obtain the this result. So here we define the J as a rho critical. So TIJ is energy momentum tensor for the matter over radiation. And we define the alpha parameter. So as we check the alpha parameter is expressed by the ratio of the vacuum energy density. The rho V is the vacuum energy density, and the rho rad is a radiation component of the universe. And also we introduce a new parameter kappa. So kappa, the kappa alpha is related this ratio can be expressed by this one. But correspond to the kappa, and this part corresponds to alpha. Kappa is defined by this. So by using these new two parameters, so we can obtain that the gravitational waves, the typical amplitude of the gravitational waves produced by the first order phase transition can be expressed by so this is the typical amplitude of the gravitational waves. And also this equation is derived by the dimensional analysis. Okay, so let's look at the numerical simulations result for the gravitational waves from the bubble collision. So this result is obtained by the numerical analysis. And so very interestingly, so the gravitational waves produced by the bubble collision. So it's expressed like this. So this is the numerical result for the gravitational waves produced by the bubble collisions. The VW is a Hall velocity. So as we can see, this naive result based on the dimensional analysis well describe the numerical result. Yeah. So this is a typical value of the gravitation produced by the first order of expansion. So when we write the prediction on the gravitational wave spectrum by using this numerical analysis, then you can obtain this gravitational wave to the first order of transition. So the most important point is that the gravitational waves from the first order of transition has a P. Therefore, so once we observe the gravitational waves with such big structures, then so we might be able to determine the dynamics of the first order of transition, or we may be able to distinguish the new physics model by observing the gravitational waves. And this gravitational wave, the form of this gravitational wave spectrum can be determined by the parameter, the beta parameter or alpha parameter. And as we confirmed, these parameters are determined by the bound solution. Alpha parameter and beta parameter are determined by the these parameters are determined by the bound solution. And bound solution is solution. Bound solution is one solution of this field equation. And the important point is that this differential equation has a potential, infinite potential. Therefore, so by using the gravitational wave observation, so we can discuss the constraint on the structure of the Higgs potential. So therefore, the gravitational wave we can use the gravitational waves as a product of the Higgs sector. One unit. Therefore, the gravitational waves are very useful to discuss the new physics. And then, so I will discuss the typical frequency of the gravitational waves. Typical frequency. So, the gravitational wave field does not have a mass. Therefore, the gravitational waves generally operate this relation. So this relation is valid when we consider the radiation component dominant unit. The frequency is determined by the inverse of the scale factor. Therefore, the gravitational waves at today F0, so it is determined by this formula. So FDN is the gravitation, the peak frequency of the gravitational waves when the gravitational waves just produce. So since the redshift effect, the redshift affects the structure of the peak frequency, therefore, so we should take into account the temperature dependence of the scale factor. And by evaluating this factor, so we can obtain the by evaluating this form factor carefully, so you can obtain this form. So if the Tn is around 100 GeV, it corresponds to the electroweak phase, the typical scale of the electroweak phase transition, and we take this as 100. And also, so when you solve the bound solution in severe extended Higgs model, then the beta over H is typically given by around 100 or 10,000. So by using this fact, so peak frequency of the gravitational waves when which comes from the electroweak phase transition is typically given by the the 100 millihertz. Therefore, the prediction of the first order phase transition is around it's over 100 millihertz. So this is the prediction in the first order electroweak phase transition. Therefore, so once we observe gravitational waves, which has this peak amplitude and this peak frequency, then so such gravitational waves might be produced by the first order electroweak phase transition. Therefore, by observing the amplitude and peak frequency, so we can distinguish the typical scale of the first order phase transition. So finally, I'd like to discuss the application of this lecture. So the application. Initially, so in this talk, we focus on the nanograph result. So in order to show the usefulness of my lectures, I'd like to discuss the correspondence between the result in our lecture and the prediction, the observation at the nano. So I think that as you may know, recently the nanograph observed the stochastic gravitational waves, and typical they observed that the stochastic nanograph observed the stochastic gravitational waves with the typical frequency is around the nanometers. So by using this formula, and so we can discuss whether the electroweak phase transition can be explained the nanograph result. So by using this formula, and also the E is around 1 nanometer scale, and beta parameter around 100, and one is around 100. Then by using this formula, so we can discuss the nucleation. We can determine the nucleation. So the nucleation temperature is around 100 MeV, mega electron. So therefore, if we consider the new physics model with the first order phase transition, so whose typical temperature is around 1 MeV, then the electroweak phase transition might explain the result at the nanometer. So, however, unfortunately, such a phase transition cannot be realized because when the first order phase transition realized, and we have confirmed the phase transition can proceed the tunneling effect, and then the latent heat is produced by the first order phase transition. And the latent heat, the typical scale of the latent heat is around the depth scale. So therefore, once the phase transition occurs, then the heating effect from the first order phase transition plays an important role. So as a result, on the other hand, the typical temperature scale is 1 MeV. Therefore, such phase transition cannot be realized because of the latent heat by the first order phase transition. Because if such phase transition occurs, then the first order electroweak phase transition affects the mechanism of the Big Bang nucleosynthesis. Therefore, such scenario can be excluded by the BBN constraint. Therefore, we cannot explain the nanograph result. Unfortunately. quantity, then another result cannot be explained by using the first order electroweak definition. So this is the application of my lecture. So I think that once you understand the analysis of the phase transition, I think that you can discuss the interesting topics of the particle. Okay, so that's all. So thank you very much.
Question or comment?
Yes.
Omega spectrum.
This one? Mm-hmm.
So could you explain qualitatively what determines this slope on the left side and right side? What is the power of F2 from power, roughly? And what determines it?
So, sorry, I forgot the peak. I forgot the.
Is it, I mean, can you give some qualitative explanations based on some analytic expression?
Mhm.
Or is it just result of a calculation, numerical calculation?
This is a numerical calculation result.
But isn't there any qualitative understanding based on some approximate analytic?
You mean that can we get the frequency dependence of the gravitational waves? Yeah. So I think that if you
Oh, you don't have to answer right now.
Yeah. So.
If you're tomorrow too, right?
Mhm, mhm.
So, I wonder what is the slope and what is the power of the system on the left side and right hand side. And what how is it determined?
Sorry, I forgot
That's
the
one
express value.
question. Another question is when you consider the tunneling in the early universe, do you include the gravitational effect or not?
You mean that did we consider the gravitational effect to the tunneling? You mean?
During the tunneling.
A gravitational effect to the tunneling process.
Yeah.
So that's a very interesting point. But I think that almost theoretical papers, so they did not consider the gravitational effect to the tunneling process. I think. Yeah, that work is I think very interesting. And I forgot the peak the power of the gravitational waves. But I think that we can check the power of the gravitational waves by checking the paper by Caprini. So yeah.
Any other question? Now let's thank you again. Thank you very much.
Thank you very much.